Hi class, this video is on topic E4 and it's on beats, resonance, music, and the Doppler effect. So these are the 4 topics that we're going to cover within this lesson. So for the first topic, acoustical beats, we need to review wave interference first. So recall that when you have more than one wave in a region of space, those waves are overlapping and the principle of superposition applies, which is that at any point in the amplitude of the resulting wave is the sum of the amplitudes of the individual waves. And if 2 waves are perfectly in phase, that is to say that the crests are perfectly line up, all crests perfectly line up, and all troughs perfectly line up, we get constructive interference. And if crests perfectly line up with troughs, we get perfect destructive interference. And when the nodes line up easily, when the nodes line up, it's easy to see how the 2 waves superimpose. If the nodes line up perfectly, wavelength and frequencies were exactly the same. However, what happens if we shift just not to a perfect destructive interference? So we have a phase shift that is not half a wavelength, or if the 2 frequencies were slightly different. If the 2 frequencies were slightly different, we do not have the nodes lining up. And seeing how they superimpose is a little bit more complicated. So let's take a look at the interference of 2 waves that have slightly different frequencies. So notice the blue and purple waves. They have slightly different frequencies. And maybe it's not obvious at first, but if you take that from this notch to this notch is like 1 second. If you count the purple waves, you have 1, 2, 3, 4, 5, 6, 7, 8. That's 8 crests in 1 second. So that's 8 hertz. And if we do that for the blue, so let's locate a crest. 1, 2, 3, 4, 5, 6, 7, 8. Hang on. Okay, yes, 9. So we got to 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 crests in a second. That's 9 hertz. So the purple one has 8 hertz. The blue one has 9 hertz frequency. And that's a slightly different frequency. So when we look at how they overlap, we are going to map it out in orange. So for the orange, which is the sum of amplitudes, sometimes their crests line up and we get a large amplitude. There's perfect constructive interference here. And sometimes we get the crest and the node line up, and that's perfect destructive interference. And notice that there's alternating constructive, destructive, constructive, destructive. Remember that in sound, amplitude is the loudness. So the way that we would hear 2 slightly different frequencies is by a sound that gets louder and then softer, and then louder and then softer. And I'm going to show you what this sounds like. Okay, so we're going to go over to a little demo. And just making sure that my computer sound is connected to this video. Okay, so, wait a minute. Sorry, that was not the right. Oh, there we go. Okay. So let's rewind that. We have a 238 hertz tuning fork. And we have, oh, did I miss the first one? Okay, we have a 250 hertz tuning fork. We also have a 238 hertz tuning fork. Separately, we don't hear beats, but when we hear them together, we hear this interesting sound effect where the volume gets louder, quieter, very quickly. So that would be hearing acoustical beats through tuning forks. I'm just trying to see which slide I'm on here. So the beat frequency is the frequency of beats produced by the interference of two waves with slightly different frequencies. We just do the subtraction of the frequency. The difference in the two frequencies gives you how frequently we will hear the beats. So how frequently you hear loud, soft, that is as frequent as the difference between the two frequencies. Notice if note if the difference in the frequencies was as big as 100 hertz, you would actually hear two notes played together at the same time. And in music, that's called a bridge. It's like a chord. A chord is 3 notes, but a bridge would be just 2 notes. So you hear 2 notes played at the same time if they're really far apart. But if they're just slightly different frequencies, then your brain detects this loud, soft, acoustical beats. And musicians use this equation in order to tune an instrument. So for example, if a string is has 105 hertz sound properties, if we were to tighten, we need to tighten it just a little bit. If we played 106 and 105 together, then 1 time per second we would hear a beat, an acoustical beat. So these are acoustical beats, not rhythmic beats. So yeah, maybe it's not exactly what you thought it was going to be. So I'm going to show you another demo of beat frequency. Instead of using 2 tuning forks of slightly different frequency, we're going to use electronic tones. So let me just get to the website. Okay. So I'm really hoping that you see these 4 buttons. And the first button is just a 330 hertz tone on its own. So that's what that sounds like. Now, on the next button plays 330 hertz and 331 hertz note at the same time. So we can actually hear that 1 time per second, we hear the volume going loud and then soft. Now, if we increase the difference between the frequency, so we have 330 and 340 hertz played together, we're going to hear a more frequent changing of the volume, loud, soft, loud, soft. So listening to the difference again. That was, the beats were 1 hertz frequency. Now it's 10 hertz frequency. So going back to our slides, let's try a problem-solving question involving acoustical beats. So we have a 360 hertz tuning fork that produces 8 beats in 2 seconds when sounded with another tuning fork with an unknown frequency. And when the unknown tuning fork is loaded, so let's say we add a very small amount of silly putty to the fork, so we add a very small amount of mass. Since it's heavier, it's going to change the frequency of vibration. And then we sound them both together again, and now we hear beats at a frequency of 3 hertz. Determine that unknown frequency. And hint, when the mass of the tuning fork is increased, when the mass of the tuning fork is increased, the frequency decreases. Okay. So I'm drawing a diagram. We have a tuning fork, it's 360 hertz. We have another tuning fork, we do not know its frequency. And at first, when we play them together, we have a 4 hertz beat frequency because its frequency is a number of events over time. So 8 beats divided by 2 seconds is 4 hertz. So the difference between F1 and F2 is 4 hertz. Then when we add mass to this one, so when the frequency goes down, we know that the beat frequency changes to 3 hertz. So just with the first piece of information, do we have enough to solve? So if the first frequency is 360, the second frequency without the mass must be 364 or 356. So we add or subtract 4. So we don't know which frequency is higher, but we know it's 4 units away from 360. Now when we add mass, making the frequency lower, the difference between the two is only 3 hertz. Which one of these, when made lower, could be 3 units away? So I like to think of it as a number on a number line. So 360 is the one we know, and we're either at 356 or 364 for the other tuning fork. For that unknown tuning fork, when we add the mass, we decrease the frequency. So when we decrease either of these numbers, which one has a difference away from 360 that is 3 hertz? And it's worth noting that when we add the mass, it only decreases the frequency a little bit. The answer is 364, because when at first 360 and 364 are 4 units away, and then when we decrease this number, we get 363, which is 3 units away. Sometimes for students, it's really confusing because there's not like a plug and chug math equation to solve for this. And instead, if you think of this, there's sort of like a logic puzzle that helps. So let's say Jonas and Lisa are gonna go to prom together. And the difference in their height is 4 inches. So I'm not telling you who is taller, but the difference in their height is 2 inches. And then Lisa is dancing the night away and she wants to take off her high heels. When she takes off her high heels, decreasing her height, now the difference between their height is only 3 inches. Who originally was taller, Jonas or Lisa? So in this case, these are like the 2 people, and Lisa takes off her heels and becomes an inch shorter. Well, she must have been the taller person, because if she was shorter than Jonas when she takes off her heels, then the difference is going to be bigger than 4 inches. I don't know if that helps anybody, but for some students it seems to help. So you can think of it in that way, the analogy, to solve those problems. Okay, so to summarize that topic, acoustical beats are an interference pattern formed by 2 waves with nearly identical frequencies. You can hear acoustical beats by a periodic change in sound intensity, and many musical instruments can be tuned using these acoustical beats. The next topic is resonance. So maybe you would think of the word resonance in everyday life. You would say, oh, that resonates with me, if there's like a match between what your thoughts are and what's being said. So I want you to think of resonance as like there's kind of like a matching. There's like a perfect condition. So a wave's amplitude can be increased when a resonance condition is achieved. All materials have frequencies at which they vibrate most easily, and that's called the resonance frequency. And as an example, let's say a kid is on a swing, and they're doing their best on their own to maintain the height the maximum height of their swing, but they want you to push them so that they can go higher. You have to push them at the right timing for that child to be able to go higher. So you have to push them. The person reaches the maximum height on the side that you're on, and then you have to push them just as they start going the other way. There's no point in that wave that you can add the push for it to be helpful. You can actually stop the person from swinging if you push them forwards when they're going backwards. It would decrease the amplitude. So for increasing that amplitude, you have to give the push at the right time. So that's the resonance condition. You have to find the resonance condition, and that's what will help amplify. When the frequency of the swing pushes, the swing push matches the natural vibration frequency of the swing, then the child's swing system is in resonance. So as we said, the amplitude can be increased when the resonance condition is achieved. Let's say if over time we increase the frequency that we are, we increase the frequency for a certain material. If we increase the frequency, we'll be able to find a place where that frequency makes the object vibrate. So another application of this, let's say you're driving, you're on a road trip, and you hear this rattling of the window, and the driver says, "Close your window, that's bothering me. I hear that rattling." And then you look at the window and you're like, "I thought that was closed," but the window was slightly open. You shut the window, you make the action to shut the window, and it does actually close a little bit. So the window, the speed of the car was perfect for amplifying the natural vibration frequency of the window. And this is an important, phenomena that it has to be taken into consideration for things like designing bridges and other like structural design, because you could break the object if you don't think about resonant frequency. So speaking of breaking objects, there's this thought that you could use your voice to shatter a glass. Now, I just want to be really clear here. I am not recommending that you do this at home. In fact, I'm begging you not to try this at home. This is not like a TikTok challenge. This is just a vocal coach kind of explaining that to you, why you might be able to, and then he tests it. So let's take a look at this short video. Okay. So let's start from the beginning.
Hey, I'm vocal coach Jamie Vendera, and the truth is, you can shatter glass with your voice, and I'm going to show you how. One of the greatest singers of all time is Ella Fitzgerald. And what Ella did in the 70s or 80s was she appeared on a commercial where she's singing, and there's a wine glass sitting there in front of an amplifier, and as she's singing along, pow, it explodes. Ella actually shattered it using amplification. With me, I actually just hold them in front of my face, no amplification, and scream until they shatter. Shattering glass with your voice comes down to two things: frequency and amplification. It takes an extreme amount of volume. Well, the average human can do probably 80 to 85 decibels, and to shatter a wine glass with voice alone, it takes at least 105 decibels, and I've been measured at right around 120 decibels. You've got to hit the exact, precise tone, frequency of that glass. And the way that you can tell that frequency is flick the glass, rub your finger across the top, and you listen really closely. So, and did you hear how it was ringing? Shattering glass is extremely dangerous, so please do not try this at home. If you're just an average singer and you're screaming at a wine glass, you could blow out your voice. You could damage your vocal cords. Now, I've been cut on the face, I've swallowed glass, I've been cut on the neck, I've been cut on the arm. I can do this because I'm a trained professional. Okay, so enough talking. Do you guys want to see this or what? Now, remember, wear safety glasses. And that's how you shatter glass. I'm Jamie Vendera, and the truth is, you can shatter glass with your voice.
Okay, so going back to the PowerPoint. So his message was, you can, but you shouldn't. You can if you have the right amplitude of the sound wave and you have the right pitch. And the pitch has to match, that frequency has to match the natural vibration frequency of the object that you want to break. Now I'm just going to reset here. I want to really make sure that we go back to the PowerPoint slides before we continue. There's lots of switching in this lesson. Okay, so that is what I have to say about the resonance topic. So now we're going to go on to music. So there's so much that you could say about the science of music. This is just a really high-level view. Unfortunately, we don't have enough time. We never have enough time in this course to cover the sound and waves unit as much as I would like. But let's talk a little bit about music. So when you're playing a musical instrument, you are playing with these elements of music. Music is made up of notes, and each note you play has a pitch. That's which note you're playing, how high or low the note is, and that's determined by the frequency of the sound wave. Then there's the duration of the note. So how long is that note heard? How long do you play that note? There's also the dynamics. So how loud or soft, that's determined by the amplitude of the sound wave. And then how you put those notes together. Oh yeah, see different notes. As you can see, this is musical notation on a staff for, let's say, a piano. And these different notes have different frequencies. And then how you put the notes together make up the melody, the rhythm, the tempo, and which notes to play and how they're put together is both science and an art. So when I say it's a science, there are rules or guidelines for harmony and rhythm. However, it's also a creative expression, and I find it so interesting how music has so many effects on the brain. So as I mentioned, different notes have different frequencies. Every note on a piano, every white and black note on a piano has a set frequency. So for example, middle C, I believe is C4, and that has a frequency of 261.6 hertz. If you move to the next note, the next musical tone, it has a higher pitch and it has a higher frequency. So remember that we learned about standing waves. It's a special kind of wave that is an interference pattern produced when an incoming wave and its reflection interfere with each other. And the effect is that the wave appears to be stationary. And a standing wave is created in or on a string, wind, or brass instrument when it plays a note. And different frequencies give different notes. And recall how these standing waves actually look within the instrument. There are these standing waves. These standing waves may have two closed ends, two open ends, two open ends, or one open end and one closed end. So we say a fixed end or a closed end, and we'd say an open end or a free end. And this would depend on which musical instrument you are talking about. And then when the musical instrument produces this sound, this standing wave, in the space around the musical instrument, the regular transverse wave travels to your ear and you hear it as sound. So if we have a set length, we can calculate multiple frequencies that create a standing wave on that set length. For example, if we're talking about a string instrument, these are the different frequencies that are possible. We can have these different frequencies. If we're talking about other instruments, some instruments allow you to change the length of the space. So actually, sorry, we've done calculations where sometimes we're calculating the frequency in a set length. And then other times we have a set frequency and we're calculating the length. And that's, we have different instruments that could allow you to change the length of the space available for the standing wave for that set frequency that you want for that set note. And there's a specific length associated with each note. And this is normally a lab that we do in this course. We have a certain note that we play, a tuning fork over top of a column of an empty column or a column full of water, and we figure out how much water is needed so that the air above the water is the perfect resonating length for that tuning fork. So one maybe quick observation that you can do at home just to reinforce this is if you just listen to next time you fill up a water bottle or a glass. So here is the sound. I'm going to attempt to play it. Can't seem to click behind this. Bless you. Okay, here it is. Make it full view, rewind to the beginning, play. Actually, let me make sure that the sound is up all the way because I feel like the sound, okay, let's just play it. So let's play that again just to really hear it. Okay, so hopefully you can hear that. Let's switch back to the PowerPoint. Uh-oh. Resume share. Oh, okay, new share. PowerPoint. Okay, hopefully that you see that we're back in the PowerPoint slides. So, so when you're filling up the water bottle, you have that sort of a guzzling sound, and that sound is getting higher and higher pitch. And that was because our resonating length was changing, and therefore the frequency that you hear was changing. Because the natural vibration frequency is different based on a column that has a different length. Okay, let's try a calculation relating to this resonance and these standing waves in a column. So let's say we have a long column that we fill up with water. So there is air above the water and the sound can travel throughout that air. On top of that column, we're gonna sound a 440 hertz tuning fork. And the second resonating length is 0.57 meters. And what's meant by that second resonating length? So we found a first length, maybe it was here, and then we kept filling up the water, and then we found that the sound of this tuning fork was amplified at that first resonating length and the second resonating length. And it's saying the second place where you hear that amplifying sound, this tuning fork is only so loud, but when you play it over this column, there's resonance, 0.57 meters. At what air temperature was the experiment conducted? So the first thing is to draw a diagram. Draw a diagram of all the resonating lengths. So if you're going to draw standing waves where you have water at the bottom and it's open at the top, we need a node at the bottom and antinodes at the top. So the first resonating length would be when we only see 1/4 of a wavelength. The next time we can have an antinode is 3/4 of a wavelength. And then the next would be 1 1/4 wavelength. So hopefully you can see that from the diagrams. And we're at the second resonating length, so we're talking about 3/4 of a wavelength. So L equals 3/4 lambda. You can also get that mathematical statement by using the equation, ln equals 2n minus 1 over 4, where if you're talking about the second resonating length, you sub in n equals 2, and you get 3 over 4 lambda either way. Rearranging for lambda, lambda is equal to 4 times L divided by 3, and you get 0.76 meters. Then the question is asking, what is the air temperature? So we don't actually want the wavelength, we want the air temperature. Recall that there's a relationship between air temperature and wave speed, so we can use the universal wave equation to solve for wave speed, and then we can use the equation that relates air temperature to wave speed to solve for T. And our T is 4.95 degrees Celsius, and rounded to two significant figures would be 5.0 degrees Celsius. Okay, so the last topic of this lesson is the Doppler effect. And the question is, what if the source of the sound waves is moving? So when we have a stationary source, the crest-to-crest distance is constant, whether we're in front of the source, behind the source, to the left or to the right. But when the source is moving, the crest-to-crest distance is smaller than the crest-to-crest distance behind. And this means that if we want to measure the wavelength, we would either have to have the source of the waves not moving, or we would need to take the motion of the source into consideration. So here we have, for a stationary source, the crests arrive at regular intervals. Let's say this is the source of the waves and this is the observer. To the observer is going to see the crests at regular intervals. If the wave source was moving, then the observer is going to see the crests more frequently. The crest-to-crest distance is smaller in front of the moving source. And an application of this is, actually there's a short video for us to observe this. When a source of a wave approaches a stationary observer, the observed frequency increases, because remember, crest-to-crest distance, which is wavelength, is related to frequency or pitch through the universal wave equation. So the observer is going to perceive a higher pitch than the actual source, than the actual wave source. When the source is moving away, the frequency decreases. And this is how a speed radar device works, so that the police can determine if a car is speeding past the posted speed limit. Okay, there is a quick, last quick sound that I want you to hear, this video.
The Doppler effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
Okay, just sharing back to the PowerPoint. I really hope, oops, stop sharing, screen share, PowerPoint. I really hope these little audio clips are helpful for you and that you can actually hear them. These little YouTube audio clips, I'm putting a link to them at the end of the video. And I'm just adding them in here because they are my favorite videos, and I'm telling you where the source is, so I'm giving credit to these sources, and they are the favorite videos that I show during regular class. So I'm hoping that you can hear them, and if not, please visit the links at the bottom of this video. Okay. So now I think conceptually we've talked about Doppler effect, but what about how we would actually calculate how much higher the frequency is or how much lower the frequency is? There is a calculation, there is a formula for it. So the observed frequency is equal to the speed of sound plus the speed of the detector divided by the speed of sound plus the speed of the source. So by detector, I mean the observer, like you at the side of the road. And the speed of sound, we're talking about 331 meters per second plus any adjustment we have to make for if we're warmer than 0 degrees. So we use that equation, 331 plus 0.6 times time, or sorry, times temperature. And then V of the source. By the source, I'm talking about the source of the wave. So maybe this is a siren, maybe it's a person singing. So the thing about using this equation in this form, though, you just have to note that sometimes V source is negative. So V source is negative if the source is approaching the observer. V source is positive if you're receding, if you're going away from the observer. And I can never remember this if I just had to memorize it. So I always draw my diagram with the siren or the wave source on the right-hand side, and I draw my observer on the left-hand side. And because I'm right-handed, it's natural that going to the right is positive. So that's my way around memorizing this, is I just get into the habit of always drawing the observer on the left. And the speed of sound, I mentioned you have to know the specific temperature or assume a speed of sound. And then your detector in this course, I'm going to be honest, almost always the observer or the detector is stationary. So you can cancel that out to 0. But the full equation is this. So higher frequency than if both were stationary. If what's the title of this? If the source is approaching you, that's a higher frequency. And really what's happening is, oh, I think I forgot to say the original frequency. Okay. So you've got the observed frequency equals some ratio or fraction times the observed frequency. This ratio here can be equal to 1, where the observed frequency is equal to the original frequency. But the original frequency might be multiplied by a number bigger than 1. If you get an observed frequency that's higher, that would be if the source is approaching you. If the source of the wave is going away from you, then this fraction here is going to end up being smaller than 1. So if the source is approaching you, you get a fraction that is bigger than 1. F observed is bigger than the original frequency. If the source is going away from you, then how do you perceive the sound? You perceive a lower frequency. And this fraction here ends up being smaller than 1, and therefore the observed frequency is smaller than the original